Hello, today I am going to take a chapter work, energy and power. Very important theorem you have in this chapter. If you know the work energy theorem, you can solve each question from this chapter. So this is a work energy theorem. I am going to prove this work energy theorem in the only linear motion. Okay, because this is very simple to prove. As you know, work done equal to force into displacement. Okay, so here for the small work done, you can write F dot ds. Okay, how to write force? So the force you can write m into dv by dt, but in this we don't need time, so just divide dv by ds and multiply ds. So the ds by dt will be v. So here you can write this is the v. So m v dv by ds. Okay, just replace here. So the work done here dw equal to m v dv by ds into ds. If you have to find the total work done, then you have to go for the summation. So if you go for the summation or integration, so here you can write dw, this will give total work done, this equal to mass into velocity dv, because ds and ds is a cancel out. So suppose the initial velocity is a vi and final velocity is a vf. So work done equal to integration of m will come out, and here you have v into dv. So the integration will be v square by 2. So v square by 2, v initial to v final. So now you can write m by 2 v final square minus v initial square. You can also write m by m v final square minus half m v initial square. This is called kinetic energy in final, and here kinetic energy equal to initial. So now we have, this is the called work energy theorem. So work done by the external force is called change in kinetic energy. So this is the your theorem you have. So work done by the all forces, this equal to change in kinetic energy. In a simple, in one line, this is the theorem you have. This is called work energy theorem. Or you can write different work done by the conservative force, work done by the non-conservative force, plus work done by the some external force, that equal to change in kinetic energy. So if you have work done by the all forces, this equal to change in kinetic energy. And always remember, change in kinetic energy, always go for the final kinetic energy minus initial kinetic energy, because minus sign is also sometimes very important. So work done by the all forces, this equal to change in kinetic energy. In some time they will ask in the theory, work done by the conservative force, can I say change of kinetic energy? So then it depend actually. Suppose that there is no non-conservative force, and suppose that there is no external force. In this case you can say work done by the conservative force equal to change in kinetic energy, if the non-conservative force and external force is not present. But general formula, general theory for work energy is a work done by the all forces, that equal to change in kinetic energy. Now I am going to define the potential energy. Potential energy. So definition of potential energy is the potential energy of the body is defined as the energy by the body of virtue of its position. It only depend on the position, no motion in this. So that is called potential energy. So for the potential energy, always you have to define your zero level, that is called reference level. So suppose that this is a reference level where I can say this is the zero potential, and now I am going to find the potential energy for the point mass. Here is given one mass m and height is a h, and this is the rest position. So what is the potential energy? Okay, so the work done by mg here is called potential energy. So let's find the work done by the mg. So at each point mg is acting in downward direction. Okay, and displacement you have h, and this is the cos 0 degree. So here you can find out mg eh. So definition of potential energy is a work done by the external force to just bring from a point to b point. So here work done by the, this will become minus, so the work done by the external force, this equal to mgh. Okay. So the potential energy, definition of potential energy is a, suppose that if you have a point mass is a m, and g, if you have at that time, that position, gravity, acceleration due to gravity, you have g, and height from the your reference point, that is h, then potential energy will be mgh. Just go like this. This is a very important. If you, mass will be the point mass, g is a acceleration due to gravity, and h is a height from the zero level. Let's find out the potential energy of the rod. One rod is kept on the ground. This is the L length is given. Okay, this is length is given L. Find the potential energy of this rod. So here mass is distributed everywhere. So you cannot go direct for mgh. You cannot apply mgh because everywhere is the mass. So this is called variable mass. So go do one thing. Just take one element, dx element, from the x distance from the bottom. Okay. Now we have, suppose that you have question only, you have dx mass here, that is you can treat as a point mass, and x distance from the reference level. Then how to write potential energy? So go for potential energy for this element. You can write, suppose that mass of dx element is dm, g and x. How to find dm? So dm here, so the total mass, suppose that given here m, length is a L, so the mass per unit length multiply by dx. So either you can go like this, linear mass density, mass per unit length multiply by dx length. So here you can write m by L into g into x into dx. So the total for the rod, if you have to find the potential energy for the rod, then you just go for the summation or integration from 0 to L. So 0 to L, that is m by L into g x into dx. M by L into g, that is a constant, and integration of x dx will be x square by 2, that is a 0 to L. So here you can write m by 2 g and L square by 2. Okay, so L cancel, so this will come mgl by 2. So for the rod, potential energy is coming out, this equal to m, g and L by 2. So another definition I can give, center of mass. So suppose that rod has center of mass exactly midpoint of the rod, that is a L by 2. Okay, so you can replace the rod with the point mass. So total mass is concentrated at the center of mass, and distance from the reference level is a L by 2. Now you can apply the formula for the potential energy for this mass. So the m and g and L by 2. So if you have a variable mass and a rod, a string, so in this case you can go mg into center of mass from reference level, 0 level. This is the formula you have. So potential energy due to a spring. So potential energy due to a spring mass system. So suppose that if you have a one mass spring connected through the one mass m, if you apply the force in this direction, so a spring will elongate and a restoring force will act opposite to the displacement kx. So suppose that if you have displacement here dx at any time, so what is the work done is defined, work done by the spring force is very important. Work done by the external force, work done by the spring force, both will be equal and opposite, so be careful about. So now I am writing work done by the spring here. So the potential energy will be minus of work done by the spring, because definition of potential energy is work done by the external force. Okay, so careful about this. So work done by the spring is called force k into x into displacement dx, and now you can cos equal to pi. So here minus will come, minus half k x square. So work done by the spring, you have always negative. Work done by the external force will become half k x square. So the potential energy, definition of potential energy is work done by the external force, that is called half k x square. If you, so this is a formula for the potential energy, but work done by the spring always you have to write minus half k x square. potential energy, also you have formula equal to minus of work done by the spring. But potential energy is a always you have plus work done by the external force F, external force. Okay. So now potential energy you have half kx square. Let's understand in the spring mass case. So if you have a spring and mass is attached, so in this case potential energy is equal to half kx square. Okay, and kinetic energy we have already derived, this equal to half mv square. Now I am going to discuss the mechanical energy. So mechanical energy is called kinetic energy plus potential energy. Okay, at mean position, first I am going for at mean position. Mean position, it means force is a 0, net force will be 0, and velocity is a maximum. So that position x will be, what is the x that point? That point x equal to 0. So you have x equal to 0, so you can write potential energy is equal to 0 and kinetic energy, that will the maximum half m v max x square. So the total energy at that point, total energy, or you can say mechanical energy, this will be half m v max x square. Similarly, at extreme position x will be a, that is called amplitude, maximum displacement of a spring, that is a x. So the potential energy that time will be maximum half k a square. So the extreme position is defined when velocity equal to 0. So the kinetic energy is equal to 0 because velocity at extreme point is 0. So the mechanical energy or total energy at that point half k a square. Okay. So mechanical energy always conserve. So the half m v max x square is equal to half k a square we have. So at every point kinetic energy and potential energy is changing, or you can say the interchange the energy between the two, but total energy is always conserved. So let's plot the kinetic energy and potential energy. Suppose that this is you have left extreme and this is you have right extreme. So the potential energy will be maximum here, and at mean position potential energy is a 0. Similarly for kinetic energy, here you have 0 extreme position and maximum will come at a mean position. So this is you have kinetic energy, and this one you have for potential energy. But total energy at each point is a constant. So the mechanical energy is a constant. So mechanical energy you can plot like this. This is called mechanical energy, and mechanical energy you can see this is independent of position, that is a kinetic plus potential, and this is always conserved. Okay. Thank you.